An atomic bomb is one of the biggest man-made reactions that we can get. The power of this detonation is unfathomable, and the fact that it comes from the smallest thing we know is even more mind-bending. An atomic bomb takes advantage of a chain reaction of atoms splitting, releasing heat and energy in the process. But how exactly did scientists find and exploit this reaction? That's the question I started with, but then I realized I wanted to go back even further. How did we find the atom? How did scientists discover something so small and learn enough about how it works to break it apart and turn this smallest scale reaction into the largest in a little over a decade? How the atomic bomb was built and how it worked is going to be a separate video. Today, we're looking at the groundwork. What was the journey into the atom? Hi, editor Amy here, stepping in before I even introduce myself to let you guys know that I actually just finished writing that video, and it is a big one. Like, we're going all the way through the Second World War big one. So if you feel like at the end of this I have kind of not gotten into enough of the details about the fission story, it's because I wanted to save a lot of that for that big video where we talk about the bomb. It is such a fascinating story, such fascinating history. Definitely subscribe right now so you don't miss it if you are interested. But I wanted to lay the groundwork first, also for me, because I really wanted to understand the backstory and really understand the science before I started writing about something as big as the bomb. So all of that is coming, I promise. But for now, let's lay the groundwork. Let's get back to me and the atom. Hi, I'm Amy. I forget to introduce myself all the time on my own channel, but I'm an historian and author, and I'm working on a new book about the atomic bomb, so I really wanted to get my head around this background. But also, I love digging into the roots of things, especially big science topics. The bomb is about the biggest, on an earthly scale at least. And because I do history here, we're going to start our journey into the atom right at the beginning with the ancient Greeks. From there, we'll cover some of the most important experiments and steps along the way, discovering atomic masses, building the periodic table, and getting into the structure of subatomic particles. Only then can we get to the point of seeing the atom clearly enough to see how physicists exploited it. This is a big story. It's about chemistry and physics and nature, and underneath it all, human curiosity. So let's tell the story. The journey into the atomic bomb starts in ancient Greece with Leucippus and his student Democritus of Abdera. Like his natural philosopher contemporaries, Democritus sought an all-encompassing theory to explain everything in nature. He settled on the theory of atomos, which literally means indivisible. Tomos means cut or slice, and the privative alpha denotes the opposite. I was a classicist. I loved learning ancient Greek. Atomists held that all matter in the universe is made from these building blocks called atoms that were solid, hard, incompressible, indestructible, and infinite in number. Individual atoms are imperceptible and differ from one another in shape and size, which explains different properties, both physical and metaphysical. A person of sour disposition, for example, was said to be made of needle-shaped atoms. Atoms, the school said, exist in a void or an emptiness, and that void is what allows atoms to move and come together without merging. The atomists say that everything we observe is just atoms in the void. Plato and Aristotle, two of the most enduring ancient natural philosophers who influenced science for centuries, both took issue with Democritus not on scientific grounds, but on philosophical grounds. Plato rejected the notion that personal attributes were mechanical manifestations of material atoms. I also need to mention Timaeus, which is Plato's science dialogue that I somehow forgot to include in the script. In Timaeus, the titular character explains to Socrates that the properties of the four elements, being earth, air, fire, and water, can be attributed to the properties of ideal geometric atoms. These are also what have now become known as the Platonic solids. The tetrahedron is linked to fire, the octahedron to air, the icosahedron to water, and cube to earth. The fifth solid, the dodecahedron, is linked to the universe. These solids were actually really important in the history of science for centuries, but they're not really that important to the story of the atom as we're telling it today, so we can leave them here for now. Aristotle rejected Democritus's proposal because he couldn't conceive of bodies falling at the same rate through a void. Fast forward a few hundred years, and medieval Roman Catholic theologians reject Democritus because his theory was both too materialistic and too atheistic to fit with a religious framework. Democritus's atoms fell by the wayside, as frankly did a lot of scientific exploration in the medieval era. The question of the building blocks of matter disappeared until scientists started trying to understand nature not with theories, but with experiments. The first part of Democritus's theory to come under the figurative microscope was the notion of a vacuum. Galileo Galilei is often credited as the first big voice in science to accept a vacuum, but it was Robert Boyle who ran the first experiments that proved it, starting in the 1650s. As depicted in Joseph Wright's famous experiment on a bird in the air pump, Boyle put a bird in a chamber and used an air pump to remove the air, creating a vacuum and killing the bird, to the mixed fascination and horror of onlookers. Boyle's interest wasn't in the macabre. He was interested in quantitatively exploring the elasticity of air divorced from any philosophical issues like what was it made of. To this end, he ran another experiment. He poured mercury into the open end of a closed J-shaped tube, then forced air into the short side. The air contracted under the pressure of the mercury. Doubling the height of the mercury column, he reasoned, would double the pressure and halve the volume of air. Tripling the mercury would triple the pressure and cut the volume of air into a third. That the pressure and volume of a gas are inversely proportional is still taught and is known as Boyle's law. I also just wanted to point out that I actually did all the animations for this video. I'm starting to learn After Effects just so I can do stuff like this. Also, a lot of my animations are for illustrative purposes only. I tried to replicate setups as best I could, but oftentimes it's just to kind of give a visual representation of what's happening. So don't take all of them as like exact fact in terms of setup. Just want to like lay that out there. Boyle picked up Democritus's core idea of immutable atoms, but rather than having differently shaped atoms make different things, Boyle posited that all matter was made of solid particles arranged into molecules, and that it's these molecules that give different materials different properties. All things, he said, are made of one Catholic matter common to them all, and differ but in the shape, size, motion or rest, and texture of the small parts they consist of. So the air he was experimenting with, in his understanding, was actually made of molecules that were themselves made of atoms. Boyle offered two explanations for air pressure. The first said that air particles coil or compress like springs, never touching through some type of repulsive force. The second posited that air is made of particles pushing each other away after physical impacts. Isaac Newton took Boyle's first explanation and added a mathematical proof showing that the repulsive force of air pressure is inversely proportional to the atoms' distances from one another. And of course, he had a lot to say about forces. He described gravity as the attraction of particles to one another with a force that varied by the object's size and distance. Bigger objects have a stronger pull that gets weaker the further you are, which began explaining how the planets in our solar system orbit the sun. He also laid out 3 laws of motion in the Principia Mathematica, written in 1687. The first is inertia. An object at rest remains at rest, and an object in motion remains in motion, unchanged until something acts upon it. The second is force. An object's acceleration depends on the mass of the object and the amount of force applied. The third is action and reaction. When one object exerts a force on another object, the second object exerts an equal and opposite force on the first. On the matter of atoms, Newton wrote in Optics in 1704 that it seems probable to me that God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles. These primitive particles, being solids, are incomparably harder than any porous bodies compounded of them, even so very hard as never to wear or break in pieces, no ordinary power being able to divide what God himself made one in the first creation. Newton's rules were so simple, his mechanical worldview so widespread, that we can't tell this story without him. Newton became foundational for science, so much so that new discoveries and lines of inquiry were made with his laws in mind and an expectation for results to align with his physics. So in the early 1700s, atoms underlying all matter are generally accepted to be uniform and conform to Newton's laws. It might seem counterintuitive, but our journey into the atom has to take a brief jaunt into the world of chemistry. In the 1700s, chemists started looking at individual elements to understand nature, which means our next big step is looking at how scientists discovered elements' properties that led to the periodic table. In the 1790s, French chemist Joseph-Louis Proust studied compounds and developed his law of definite proportions. All chemical compounds contain their fixed proportion of material by mass. Copper carbonate, for example, always has 5 parts of copper, 4 parts oxygen, and 1 part carbon. The atoms making up those elements, copper, oxygen, and carbon, were still the smallest possible units of matter, indivisible and immutable, and their ratios were always the same in a given compound. Proust inspired English chemist John Dalton to marry ancient Greek philosophy with modern scientific theory, which, remember, is very Newtonian. Dalton wanted to know why the gases that make up our atmosphere don't separate into layers. He posited that atoms aren't infinite in type, but rather that each element has one atom, and that all atoms of a given element have the same mass. In 1803, he started classifying elements by assigning weights to atoms beginning with hydrogen as the lightest. He assigned it an atomic number of 1. From there, he used compounds with hydrogen to assign weights to other elements. So, in describing water, for example, which is a compound of hydrogen and oxygen, he found that 1 gram of hydrogen reacts with 8 grams of oxygen to make water vapor, a reaction he assumed was some type of attractive force binding the elements together. From there, he determined that the mass ratio of oxygen to hydrogen was 8:1, so he assigned oxygen an atomic number of 8. With our modern understanding, we can see a problem here. Dalton assumed that molecules of a given element are single atoms, so he thought water was made of 1 hydrogen atom and 1 oxygen atom. We know that's wrong. It's 2 molecules of hydrogen to 1 molecule of oxygen, or H2O. But for his purposes of bringing consistency into chemistry, it didn't matter too much because his results didn't depend on knowing whether atoms were individual or joined together as molecules. Dalton also discovered, very importantly for this story, the law of multiple proportions, which states that if 2 elements combine to form more than 1 compound, the ratio of the mass of the second element is a small whole number of a fixed amount of the first element. Let's explain that in English with an example. Carbon and oxygen can combine to make 2 different chemical compounds. For the first, we need 100 grams of carbon and 133 grams of oxygen to make carbon monoxide. For the second, we need the same 100 grams of carbon, but with 266 grams of oxygen to make carbon dioxide. Dalton showed that carbon monoxide has 1 oxygen atom for every carbon atom, while the CO2 has 2 oxygens per carbon atom. What this tells us is that Dalton was working with discrete bits of an element. He just didn't know what that meant yet. Dalton's assumption that the force binding elements together was some sort of attractive force was also wrong. We know that now. But with no better explanation for what he observed at the time and Newton backing him up, his work was widely accepted and served as stepping stones for his contemporaries and followers. 2 of these were German naturalist Alexander von Humboldt and French chemist Joseph-Louis Gay-Lussac, who first discovered the volumes of hydrogen and oxygen needed to combine to make water. What they did, and predominantly Gay-Lussac, was apply Dalton's idea about chemical masses to the volumes of gases. This work led to Gay-Lussac's law of combining gases. The first part of this law says that when gases combine chemically, the ratios are numerically simple. Let's take the example of nitrogen oxides. Gay-Lussac found that nitric oxide, nitrous oxide, and nitrogen dioxide each have the corresponding volume of their constituent gases. It was an expression of volumes of the chemical constituents of a compound. The second part of Gay-Lussac's law explains that if gases combine to form other gases, the volume of that new gas is a simple numerical ratio of the original volume. Gay-Lussac's example was combining carbon monoxide and oxygen to make carbon dioxide. He noted that one given volume of carbon dioxide is made of 1 portion of carbon monoxide and twice that volume of oxygen. In his own words, gases, in whatever proportion they may combine, always give rise to compounds whose elements by volume are multiples of each other. Again, from our modern standpoint, we can see a problem. There's an extra oxygen molecule. Carbon monoxide and oxygen don't make carbon trioxide. What happened to the other oxygen atom? Gay-Lussac didn't know how or what, but he did see that his result went against the accepted understanding of the atom as the smallest possible unit of matter because something happened with that third oxygen atom. Italian scientist Amedeo Avogadro also built off Dalton's work. He wanted to know whether atoms and molecules were different, and if so, how many atoms and how many molecules were in a volume of a given gas. In the early 1810s, he theorized that individual molecules of a gas are made up of multiple atoms, what he called the diatomic model. Gaseous oxygen, Avogadro said, is composed of molecules of oxygen rather than individual atoms. This explained Gay-Lussac's result. Each oxygen molecule has two atoms, and one of those molecules splits so that each carbon monoxide compound gains an oxygen atom to become carbon dioxide. Unfortunately, Avogadro was not the best writer, and his theory of diatomic molecules was ignored for decades. It didn't gain traction until September of 1860, a full 50 years later, when Italian chemist Stanislao Cannizzaro presented the theory at a conference in Karlsruhe, Germany, a conference where chemists were meeting just to define terms like molecule and atom once and for all. Consistency in chemistry was a big thing here. Cannizzaro presented Avogadro's theory of diatomic molecules and suggested that if a molecule can consist of two atoms of the same element, it would help chemists determine atomic masses and finally classify elements. When German chemist Lothar Meyer heard this, he said, "It was as though scales fell from my eyes, doubt vanished, and was replaced by a feeling of peaceful certainty." This theory made sense, and within a few years, Avogadro's hypotheses were widely accepted by chemists. Scientists now agreed that each element has one type of atom, and those atoms can join to make molecules. Atoms or molecules of different elements can combine to form compounds. At the root of this was mass. The mass of the atom was a crucial part of classification. Meyer took his newfound clarity and developed one of the first modern periodic tables, organizing elements by mass while keeping elements with similar properties grouped together, leaving gaps for new discoveries. French geologist Alexandre-Émile Belguillet de Chancourtois realized the periodicity of elements when arranged on a cylinder, but his telluric screw model was so hard to read and use that it never gained traction. I mean, it's impossible. I just wanted you guys to see it too. Russian chemist Dmitry Ivanovich Mendeleev developed his own system, classifying elements by weight and type, skipping hydrogen because it didn't fit nicely. Mendeleev found that when he arranged elements by increasing atomic weights, they form a periodic structure in chemical properties. Like Meyer, he also left gaps because, according to that periodicity, he was sure new elements would be discovered as atomic weights increased. When chemists discovered the first non-reactive noble gases, it seemed to affirm Mendeleev's hypothesis. It was becoming clear that there is some underlying structure common to all elements. It just wasn't clear exactly what that was yet. But the more chemists learned about atomic weights, the more they could reveal the full table. So here we are in the late 19th century. Scientists generally accept that gases are made of molecules of elements and not singular atoms. Knowing this helps them not only to understand elements, but to classify them. But the atom itself is still a mystery. Scientists need to dig deeper and explore the pressure, volume, temperature, viscosity, and heat conductivity of gases to really understand the elements and the underlying atoms that make them. We can't see the atom yet, but scientists are gaining indirect evidence of what it is. But what's wild at this point is that even though scientists accept that atoms exist, the lack of direct evidence made some people think they're not actually real. Everything was indirect. So even people like Mendeleev, for quite a while, thought atoms were helpful for calculating things and classifying elements, but were ultimately just a theoretical tool. The good news is, this didn't stop scientists from accepting atoms and working with the theory, because even if treated as a theoretical device, they were helping unlock nature's secrets. But things got messy. The more scientists dug, the more complicated atoms got, especially when it started to look like they weren't actually the smallest building blocks of matter. Before we continue, we're going to take a brief brain break with an ad break. Swiss mathematician Daniel Bernoulli is our next important figure. Bernoulli imagined a volume of a gas as a group of particles moving quickly and chaotically in an enclosed space. From there, he reasoned that the pressure of a gas came from those particles pressing up against the wall of their container. Then he looked at what was happening when the gas was heated and found not much. Heat made the molecules move faster, but it didn't affect the gas's pressure. The effects of heat are distinct from temperature. Heat affects the molecule's movement, while temperature measures how heat flows from one body to another. Bernoulli's so-called kinetic theory of heat was largely ignored throughout the 18th and early 19th centuries because it went against Isaac Newton's widely accepted view that gas atoms repel one another. I told you guys Newton's influence was a big part of this story. Chemists tried desperately to explain heat in a way that fit into Newton's framework, and Scottish chemist Joseph Black managed it with the caloric theory of heat. The caloric theory says heat is an indivisible substance permeating matter, effectively a fluid. The theory didn't last. In the early 1800s, German physician Julius Robert Mayer and then English physicist James Prescott Joule both demonstrated that heat is a form of energy. Heat was explained as the motion of matter. The speed of particles is what generates heat. The kinetic theory returned and was soon buoyed by mathematical proofs, and it supported atomic theory. If heat was the random motion of atoms bouncing around and transferring energy, something had to be carrying that heat energy and transferring it and taking it up. That something was likely atoms. Or maybe part of an atom is carrying that heat energy. It's the first hint, and a still very indirect hint, that there might be something smaller making up the atom that's the building block of all matter. It's also the first time that one of Newton's long-accepted explanations is found to be wrong. Next, we need to meet English physicist and chemist Michael Faraday. Chemists already knew that water in which salts were dissolved could carry a current. This is referred to as an electrolytic solution. In the 1830s, Faraday set up an experiment to explore this current. He placed two electrodes, a positively charged anode and a negatively charged cathode, in the electrolytic solution in a voltaic cell. When he ran a current between the electrodes, he observed a chemical reaction where material formed on the electrodes. He basically made a battery that stripped charged atoms called ions from one metal and added them to the other. He found that the same thing happened regardless of the solution or the type of metal he used. What mattered was that the current stayed the same. Faraday further discovered that ions of a given chemical compound have the same charge, and that charge is always a whole number, never a fraction. In his words, the atoms of matter are in some way endowed or associated with electrical powers, to which they owe their most striking qualities, and amongst them their mutual chemical affinity. That charge, the amount of energy needed to produce 1 gram of a material, was eventually called a Faraday, or the Faraday constant, which scientists later determined is equivalent to the charge of 1 mole of electrons, a mole being 6.022 times 10 to the power of 23. Faraday, the man, continued his experiments, and in one, he measured that 1 Faraday of charge passing through water releases 1 gram of hydrogen and 8 grams of oxygen, which is the same ratio that Dalton found. But Faraday's measurement was more precise because it was more than just the ratio by mass. He found the ratio of the masses of atoms to the electrical charges of ions. The significant part is the charge. For the first time, scientists really start to consider that matter might carry a charge and that ions could be a smaller part of the atom that carry that electric charge. The same way Dalton exposed vital parts of the atom with the chemical combination of gases, Faraday started to expose new properties of the atom with electricity. So now we're poised to move on to the realm of light and electricity with Scottish physicist James Clerk Maxwell. In the 1860s, Maxwell determined that light is an electromagnetic wave. Put simply, it's the flow of energy through space, and the changes we see in color are really changes in frequency of that wave. Longer waves on the red end and shorter on the violet end. But it goes beyond what we can see. The waves keep getting longer past red and shorter past violet, but for the moment, we don't know what's on the edges of the spectrum. German physicist Joseph von Fraunhofer dove into the electromagnetic spectrum when studying sunlight. He used a prism on a telescope to break apart sunlight into its composite wavelengths and found hundreds of dark bands. He labeled the most prominent bands in the sun spectrum with the letters A through G, what we now call the Fraunhofer lines. Building on Fraunhofer's work, another German physicist, Gustav Kirchhoff, heated different elements to incandescence and studied their colored vapor with a spectroscope and found that each element had its own unique pattern of these absorption lines, or spectral lines. I just want to make some terminology abundantly clear. So we're talking about the visible light spectrum right now. We're not worried about microwave ends or X-rays. So the full visible light spectrum is the full spectrum. When we're talking about an absorption spectrum, it's the wavelengths of light that are absorbed by atoms in a gas. When we're talking about the emission spectrum, it's the frequency of light that that gas emits as light when it's heated. So if you line up the emission and absorption spectra of an element, they will match. The same bands missing in absorption as showing in emission. Also, just a friendly reminder that my animations are for illustrative purposes only. Thank you very much. Kirchhoff and fellow German Robert Wilhelm Bunsen found 2 new elements this way, cesium and rubidium. And what's really important about spectral lines is that for the first time, we're directly seeing atoms interacting with nature. We're seeing the effect of atoms on light. We just can't exactly see what that interaction is yet. Fraunhofer expanded on his observations and posited that all pure elements emit and absorb light at specific frequencies or wavelengths. Swiss mathematician Johann Balmer took Fraunhofer's idea and applied it to the emission lines of hydrogen. Hydrogen gas, when excited, emits light lines of set colors or wavelengths, and we can see without any math that the lines get closer together as the wavelengths get shorter as it gets to the violet end of the spectrum. Balmer developed an empirical formula that explained the visible spectral lines of hydrogen and found the mathematical constant is a constant of proportionality. In English, he found the mathematical expression that explained the wavelengths getting closer as the proportional change. Swedish physicist Johannes Rydberg generalized Balmer's results and guessed at a formula that would match the mathematical pattern. The Rydberg constant fit the observed spectral lines of hydrogen. Scientists eventually realized that the missing colors in the sun's light spectrum were because those wavelengths were absorbed by atoms. Atoms, scientists realized, absorb light and emit light, but only at isolated frequencies. These emission and absorption spectra, along with the formulae that started explaining them, were big clues that maybe we have a tenuous grasp on something. The problem was these constants break down at more complicated elements. The Rydberg constant worked for hydrogen, but it couldn't explain any more complicated elements. But because it worked for hydrogen, it gave scientists a starting point from which to dig deeper. This is a weird way that scientists approach problems like this, at least at the time. Start with a formula to explain the simplest element, then try to make it work for other things. It's a bit backwards, but it's a start for a methodical investigation, especially when you consider the era. Everyone knew atoms were going to be complicated, so starting with a set of rules that worked for the simplest atom meant they were probably on the right track for a more general theory. All of this, coupled with Faraday's work, brings us to a point where we know atoms can emit, absorb, and carry an electric charge, because remember that light is an electromagnetic wave. But what exactly that energy is, and how it works, is still a mystery. Continuing his work into electricity, Faraday set up a simple experiment where he ran electricity between a cathode and an anode enclosed in a tube so he could create a partial vacuum or fill it with different gases. Studying the spark jumping between the electrodes, he found that sometimes there was no spark, there was a glow instead. Among the scientists who worked with the same setup was German physicist Julius Plücker. Plücker found that a better vacuum created a better glow that reached the wall opposite the tube, and that bringing a magnet close to the tube distorted the glow, suggesting it was some kind of magnetic disturbance. Plücker's student Johann Hittorf found that an object in the tube led to a shadow cast in the glow, suggesting the effect was a ray. English physicist William Crookes did the same experiment and found these rays were bent by a magnetic field, suggesting they carried a charge. Crookes also found that with a low-pressure gas in the tube, there was a glow regardless of the type of gas or the metals used. The glow, eventually called cathode rays, was a property of the electric current itself. High-energy electrons from the cathode hit gas atoms in the tube, excited them, and caused them to emit the glow. But cathode rays were doing too many things: glowing, casting shadows, being impacted by magnets, carrying a charge. Scientists disagreed on the basic nature of cathode rays. French and British physicists generally agreed that they were electrically charged particles because the beam was affected by a magnet. German physicists fell on the side of cathode rays being waves because they traveled in straight lines without reacting to gravity. Are cathode rays a wave or a particle? It was English physicist J.J. Thomson who settled the issue. He ran an experiment wherein he passed cathode rays between two parallel aluminum plates. When the top aluminum plate was negatively charged, the cathode ray moved down away from it. When the upper plate was positive, the ray moved up. Because he saw magnetic and electrical deflections, he determined that cathode rays had to be negatively charged particles. Electricity was a particle, he said, and he called that particle an electron. In another experiment, Thomson put two magnets on either side of a cathode ray tube and found the ray was deflected. Using the electric and magnetic fields together, he calculated the mass-to-charge ratio of the cathode ray particles, of the electrons, and found the mass of each particle was much less than an atom. A single electron was nearly 1,000 times lighter. It explained previously confusing observations like cathode rays passing through a metal sheet and electric current flowing through a copper wire. He also calculated the velocity of the electron and found it was about 30,000 kilometers, or 18,000 miles per second. Like Crookes, Thomson also found his results were consistent regardless of the metal he used as the source of the cathode ray. These subatomic particles had to exist within all atoms. The most important part of Thomson's results for our journey into the atom was that it finally prompted scientists to drop the 2,000-year-old idea of atoms as the smallest possible unit of matter. They were made of smaller particles. Democritus was wrong. J.J. Thomson next worked with energized tubes to separate ions and measure their mass-to-charge ratios as they hit photographic plates. When he experimented with neon gas, he found some particles deflected differently. The only explanation he could fathom was that these particles had different atomic weights. He discovered isotopes. The gas was mostly made of neon-20, but there was some isotopes of neon-22 and trace amounts of neon-21. With this discovery, John Dalton's long-standing assumption that all atoms of an element have an identical mass also fell apart. And it wasn't just neon. Of course it wasn't. British physicist Francis William Aston developed the mass spectrograph that allowed him to break a beam of ions into a mass spectrum of lines, similar to how light is broken apart by a prism. In analyzing close to 50 elements, he found that most have isotopes. We're finally starting to really get into the atom. Atoms have firm, measurable properties. They come in isotopes. They absorb and emit light. They contain electrons. But for all this work, we still can't see one. Scientists didn't know it at the time, but the wavelength of visible light is larger than an atom, so microscopes can't help. Scientists need a new, shorter wavelength of light, a new way of seeing things. And that takes us to the discovery of X-rays. Around the time J.J. Thomson discovered the electron, German physicist Wilhelm Conrad Röntgen was experimenting with cathode rays. Scientists had shown that the rays could pass through a piece of aluminum placed on a tube, and Röntgen wanted to know if they could pass through a fully obscured tube to make a fluorescent plate glow. So he obscured the whole setup in cardboard and placed a fluorescent plate a few centimeters away. Then noticed that a screen of barium platinoside across the room was glowing. It didn't make sense. Previous experiments said the cathode ray glow could only travel a short distance, and that fluorescent screen was fluorescing while not in the path of the cathode ray at all. So how could it possibly be affected? There had to be some much more excited rays of electrons coming out of the tube. He tried to duplicate the result and found that whatever this radiation was, it passed easily through materials like paper, wood, and aluminum, but affected photographic plates. And it also didn't have the usual properties of light. It didn't reflect or refract. Röntgen didn't know what to make of it, so he called the phenomenon X-radiation and used the beams to take images of the interior of metal objects and the bones in his wife's hand. The particles Röntgen found were a byproduct of the cathode ray electrons hitting the anode. The electrons are moving so fast through the near vacuum that they build up speed and then stop suddenly when they hit the anode. That rapid deceleration generates a new kind of particle with a short wavelength traveling so fast it can pass through different materials with minimal absorption until hitting a photographic plate. The plate has chemicals that can be excited by almost anything, including higher energy particles. X-radiation, or X-rays, scientists determined, were still on the same electromagnetic spectrum, just on the short end where we can't see them. French physicist Henri Becquerel thought Röntgen's X-radiation might be related to fluorescence and phosphorescence, the process wherein a substance absorbs and then emits energy as light. Becquerel chose uranium salts for his experiments to see if they might phosphoresce X-rays. He wrapped photographic plates in black paper and then put the phosphorescent material, the uranium salts, on the plate out in the sun. He theorized that the sunlight would excite the salts into phosphorescing. If there were any X-rays involved, only they would go through the paper to hit the photographic plate. Early experiments seemed to confirm his hypothesis. Then, on a cloudy day when he couldn't run his experiment, Becquerel stuck the uranium salts and holographic plates in a drawer. When he pulled them out, he expected maybe a faint impression on the plate. What he found was a sharp outline. Even without sunlight stimulating phosphorescence, he had developed the plate. The uranium emitted some kind of penetrating radiation that didn't require anything external. It wasn't long before scientists found that quite a few elements emit this kind of passive radiation. New Zealand physicist Ernest Rutherford started working with this newly discovered radiation and found that certain radioactive substances emit multiple kinds of radiation. The less powerful positively charged rays he called alpha rays, and the more powerful negatively charged rays he called beta rays. French physicist Paul Villard found a third kind of radiation that has no charge and is more penetrating than either alpha or beta rays, and he called this gamma rays. Over the course of his work, Rutherford and English radiochemist Frederick Soddy found that radiation naturally changes an atom. Working with thorium, they realized that it constantly generates a chemically different but intensely radioactive substance before it eventually disappears. Half of it decayed in 4 days, then half of that in another 4 days, and so on. They discovered radioactive decay and half-life. So let's pause here on the eve of the 20th century because we're at the critical moment. The discovery of the electron and radioactivity were both hugely revelatory and hugely problematic, especially the electron. Atoms on the whole are neutral, but the electron carries a negative charge. So something has to be balancing the electron, but what? And what is happening with radiation? The atom is clearly losing something in the process of decay, but how does the element change? And the biggest question: how is it all put together? It was like scientists had the pieces of a puzzle. They knew about electrons, they knew where atoms fell in the periodic table, isotopes, radioactivity, and absorption lines, but no one knew how the pieces went together, or if any pieces were missing. So they started working on models of the atom, thinking that if they found an arrangement or a set of rules that worked for simple atoms, they might be on the right track to finding a structure that worked for everything. It's a lot like how Balmer and Rydberg couldn't really explain absorption lines, so started with a formula that fit one element and used it as a base. We're finally at the point where scientists have enough information to start throwing atomic models at the wall and seeing what sticks. Before we see what those models were, we're going to take another quick ad break. One of the first atomic models came from J.J. Thomson, which was based on Lord Kelvin's so-called plum pudding model. In this model, the atom is imagined as a positive sphere with electrons embedded at regular intervals, like raisins in a plum pudding, making for an overall neutral atom. This was an incredibly stable model. If an electron, or a raisin, is displaced, the rest will settle back into their original positions, or as close to their original positions as possible. English physicist John William Strutt, also known as Lord Rayleigh, posited a version of the plum pudding model with so many electrons they effectively formed a vibrating fluid overlapping the positive electric sphere. Vibrating models were fairly popular. English physicist J.H. Jeans proposed a model wherein the vibrating electrons were the cause of emitted light. British mathematician G.A. Schott's vibrating model had electrons expanding to explain emitted light. German physicist Johannes Stark threw his Archeon model into the mix, which imagined the atom made of tiny magnets with the north and south poles arranged in a closed loop. Another model proposed around the same time was the Saturnian model. I somehow read Huntaro Nagaoka's name backwards when I was recording this video. I'm not entirely sure how, but I want to correct myself immediately, with sincere apologies to Mr. Nagaoka. Japanese physicist Nagaoka Huntaro imagined electrons orbiting a central mass called a nucleus. The problem with this model was its inherent instability. The continual radiation physicists had observed meant electrons were losing energy, and that meant they were spiraling into the nucleus, as per classical Newtonian physics. No electron could remain in orbit indefinitely. Without a stable atom, nothing else could be stable, but we know matter is stable, so the Saturnian model was clearly wrong. It was Ernest Rutherford who helped solve the question of what an atom looks like. He soon started using alpha particles as a tool. An alpha particle is identical to a helium-4 nucleus. It has 2 protons, 2 neutrons, and a +2 charge. He didn't know about protons or neutrons yet, but he did know that when an alpha particle hit a scintillation screen, it created a brief glow, sometimes called a kick, that could be visually counted. He also knew from past experiments that a beam of alpha particles hitting a photographic plate made a sharp-edged picture, but that same beam going through a sheet of mica just 20 micrometers thick left a blurry impression. Something was lightly scattering the particles. He didn't know what to make of this, but he thought alpha particles were part of the answer. They're smaller than atoms, they're a helium nucleus, and they're charged. He reasoned they could pass through an atom and reveal its structure. It's like throwing balls through a box to see what's inside. If the plum pudding model is correct, the alpha particles won't deflect much. The balls will roll through the empty box. If there's something bigger in there, the alpha particles will show a deflection, like balls hitting an unseen post. Rutherford was pretty sure about the plum pudding model, so he set out to confirm this with alpha particles, sending a beam through a thin foil. He imagined that the electrons in the plum pudding were so small and so far apart that alpha particles would sail right through with only a few knocked slightly off course as they came close to the electrons. He expected a minimal result. In their first experiment, Rutherford and Hans Geiger looked for alpha particles right behind the foil. They found most were scattered by about 1 degree, which they read as confirming the plum pudding model. But then one of Rutherford's grad students, Ernest Marsden, needed something to do, so Rutherford had him work with Geiger to refine the experiment. Send a beam of alpha particles through gold foil just 0.00004 centimeters thick and measure where those particles hit as flashes of light on a scintillation screen. Geiger and Marsden found that while most of the alpha particles went straight through, some, about 1 in 20,000, were deflected at varying degrees, some as much as 180 degrees. They bounced right back. As Rutherford explained it, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back to hit you. Rutherford reasoned that the backward scattering could only be explained by a single collision, and his calculations confirmed that the only way to get the observed result was if there was a small, dense, positively charged mass at the center of the atom. Because atoms are mostly empty space, the alpha particles go through, but once in a while one hits this mass head-on, or nearly head-on, and scatters. Rutherford found the nucleus. Now the atom was understood to have a nucleus with electrons orbiting that central mass. The plum pudding model was gone, and it looked like the Saturnian model was right, but there was still that pesky instability to deal with. Electrons are losing energy, but not crashing into the nucleus. It was like classical Newtonian physics broke at the atomic level. And if Newton can't explain the atom's stability, what can? Danish physicist Niels Bohr stepped in to offer a solution. Instead of imagining an atom like a little solar system, he imagined electrons orbiting the nucleus in shells, like a nesting doll, only the shells weren't solid. Bohr got around the instability by positing that electrons' orbits were stable based on energy, and that the energy of the electrons depends on the size of its orbit or how far away it is from the nucleus. The lower the orbit, the lower the energy. The electrons' orbits aren't decaying classically. They're jumping from one shell to another, losing energy in the process. That energy loss is the radiation physicists measured. Bohr's atom was completely stable in the state with the electron in the smallest orbit, since there's no lower energy orbit the electron can jump to. English physicist Henry Gwyn Jeffreys Moseley added support to Bohr's model when he studied the short-frequency spectral lines of heavy elements, frequencies closer to X-rays. He found that each element radiates X-rays on a different wavelength, and that the wavelength and frequency follow a regular pattern based on the charge of the nucleus. He called this charge the atomic number, and importantly, he found that the different series of X-rays correspond to the shells of Bohr's model. There's a little bit more to this that I wanted to explain further. So when Mendeleev, or Mendeleev, I might be mispronouncing it, devised his periodic table, he had 63 elements to work with, and his placement was based on atomic weight and observed properties to group like elements together, and he left gaps for new discoveries. It wasn't a perfect system, but it worked pretty well, and he assigned every element a number, but the number didn't really have rhyme or reason, and it just went up with every subsequent element. This number, importantly, wasn't tied to any physical property of the elements, and in fact, the order of the elements actually brought into question some of the structure because some elements didn't behave the way they should based on that order. What Moseley's experiment found was a linear relationship between atomic number and the frequency of emitted alpha rays. Moseley's work is what gives us our modern value of an atomic number. But how were the shells stable? It was Max Planck who explained it, or at least offered an explanation. Planck posited that light energy can only be emitted, transmitted, or absorbed in discrete packets he called quanta, from the Latin for how much. The best analogy I've ever read to get your head around this is milk and eggs. We can think of a flow of energy as milk pouring into a bowl. You can measure the amount you need and adjust it, add a little bit, take a splash away, but you can't do the same with eggs. You can't add half an egg to a bowl, and don't say you can separate the white and the yolk, because I mean a half of each, half of an egg. The egg is the unit. In the quantum explanation, the energy is an egg, not a flow of milk. Each quantum, or energy packet, each egg, is in turn defined by the frequency of that radiation, known as Planck's constant. So in this model, an electron moving from one orbit to another inside an atom is losing or gaining a quantum, losing as it goes in and gaining as it goes out. The atom is stable because an electron can never lose energy once it's in the innermost level. Planck was just trying to explain observed results with a theoretical formula, which we've seen a lot of scientists do on this journey. He just happened to stabilize Bohr's atom in the process. Well, he sort of did. We're back to a familiar issue. Bohr's model explained hydrogen, but nothing else. It couldn't explain more complex atoms like oxygen that have 8 electrons. Bohr's model was ultimately heuristic, but gave scientists a framework. Rutherford became obsessed with the atom, and in particular, the makeup of the nucleus. In another experiment in 1919, he bombarded a cylinder of nitrogen gas with alpha particles. The result was a series of flashes on a scintillation screen. Most were alpha particles, the same ones he was using in the experiment, but some were dimmer and smaller. They weren't alpha particles, so since they weren't coming from the beam, they could only be coming from the nitrogen gas. The alpha particles were hitting the nucleus, and instead of bouncing back, some of them were knocking something out of the nucleus. They were chipping away at it. That something might be balancing the negative charge of the electron, and he called it the proton. Physicists knew the nucleus held the bulk of the atom's mass. Remember, J.J. Thomson measured electrons as 1,000 times lighter than the atom. The periodic table highlighted the periodicity of elements, showing that various nuclei were multiples of the weight of the hydrogen atom. So physicists reasoned that the nucleus was made of bricks that were the same for every element. What differed was the number of bricks. Nuclei were clusters of this brick, which was now thought to be the proton. So now we have two subatomic particles. The nucleus is made of heavy protons, and the ultralight electrons orbit it, solid in their place because of energy. But again, this model raised more issues than it solved. Remember that atoms are neutral, not charged. A neutral hydrogen atom has an atomic weight of 1, has one positively charged proton to balance out the negatively charged electron. It fits. But helium, the next lightest element, has an atomic weight of 4. So that would mean there are 4 protons and the known 2 electrons. It doesn't balance. Uranium's atomic weight of 238 meant 238 protons to its 92 electrons. Even less sense. We have to leave Rutherford pondering the nucleus for just a moment because there's a couple of other experiments we need to touch on, the first of which is the Davison-Germer experiment. In 1924, Louis de Broglie proposed that all matter displays the same wave-particle duality as light. If electrons had a wave property, Bohr's model made more sense. Clinton Davison and Lester Germer at Western Electric ran an experiment to prove this hypothesis. They shot electrons at a crystal of metal nickel and found the electrons were scattered by the surface in a diffraction pattern. It's analogous to the double-slit experiment, but instead of shooting a beam of light through slits to see the interference pattern, you're letting that light scatter off atoms to see the interference pattern. I feel like I should jump in just to explain the double-slit experiment since I referenced it and kind of said what it is, but I didn't really get into it. So the double-slit experiment is a very famous experiment in physics, and it's the proof that light has a wave property. Basically, you take a light source and you shine it at a plate that has 2 parallel slits in it. If you imagine, as is done with this experiment a lot, light as kind of arcing waves, where the waves overlap and their peaks overlap when they hit a photosensitive screen, that's where you get bands of light. Where the troughs overlap at the screen, you get dark. So instead of just seeing the light from the 2 slits in the plate, you get this larger interference pattern. That's the double-slit experiment, which is analogous to the Davison-Germer experiment. The result was proof that matter has a wave property, confirming de Broglie's thesis. It also gave Bohr's model stability and allowed scientists to treat electrons as waves. Around the same time, in 1922, American physicist Arthur Hawley Compton did an experiment wherein he set a beam of X-rays through a target material. He found that some of the beam was deflected sideways at various angles, and some of those scattered X-rays had longer wavelengths than the original. It only made sense if the X-rays were particles with energy and momentum. The scattered X-rays had to be transferring their momentum to the electrons, shifting their frequency, and the shift in energy was a set amount, a quantum. Both these experiments support the quantum model, and Austrian-Irish physicist Erwin Schrödinger solidified quantum mechanics with a mathematical explanation. But there was still the issue of the charge of atoms and what was happening inside the nucleus. This was still Rutherford's main focus, and his running idea was that an electron and a proton could combine to make a neutral particle, but there was no way to test this theory. So scientists started looking for it. By the early 1930s, atomic physics was a growing discipline with international teams working to unravel the atom. German physicist Walter Botha and his student Herbert Becker bombarded beryllium with alpha particles from polonium and studied the produced radiation. Frédéric and Irène Joliot-Curie did the same experiment. They measured the produced radiation hitting a paraffin target and found that it knocked loose protons from hydrogen atoms, protons that recoiled at a high velocity. The French pair thought the radiation was gamma protons, but English physicist James Chadwick immediately knew this assumption was wrong. Photons aren't heavy enough to knock particles as heavy as protons loose from a target. Chadwick ran his own version of their experiment and posited that the beryllium radiation was actually a neutral particle with the same mass as a proton, a neutron. The neutron was a game changer. It explained the troubling weight discrepancy. It wasn't just positively charged protons in the nucleus, it was neutral neutrons as well, the overall positive charge negated by the negative electrons. It also explained how atoms of the same element can have different weights because of the number of neutrons. Neutrons explained isotopes. With this clear picture finally in view, there was one last goal: split the atom. It was something of an international race, with teams in America, Germany, and England all working to accelerate a stream of protons to give them enough energy to knock apart a nucleus. John Cockcroft and Ernest Walton had a setup at the Cavendish Laboratory at Cambridge under Ernest Rutherford. Their setup had an accelerated beam of protons. Protons, because they can travel deeper into the atom owing to their positive charge, aim at a lithium target. They were looking to count scintillations on a screen as alpha particles hit the zinc sulfide surface. The setup had one man in a little curtained-off observation booth manually counting the flashes. The speed was key. Across the board, physicists expected to need upwards of 1 million volts to accelerate the proton fast enough to affect the atom. On April 14, 1932, they ran their experiment with the proton accelerated by 300,000 volts and saw too many scintillations to count, so they lowered the energy and still saw a stunning number of flashes. They found a significant result all the way down to 125,000 volts. The only fathomable explanation was that they were splitting the lithium atoms into 2 helium atoms. Lithium has 3 protons and 4 neutrons, sometimes 3 depending on the isotope, and 3 electrons. When hit with a proton going at high speeds, it merged with and broke the lithium atom into 2 alpha particles, which, as we've said, are identical to helium atoms, 2 protons and 2 neutrons. That evening, they added metal foils to the setup to measure the speed and energy of the created helium atoms. Metal foils of varying thickness in the path of the produced particles could measure how long it took them to stop. Calculations revealed the astonishing figure of 8 million electron volts. The protons were only accelerated by 125,000 volts. Given the scale of the experiment, the reaction was obscenely violent. It became the first laboratory proof of Einstein's most famous equation, E = mc squared. There is, of course, more going on inside an atom, more forces and subatomic particles, but since our narrative today is moving us toward the bomb, this is where we need to be. Atoms, the uncuttable, smallest base part of all matter, aren't just made of smaller parts, they're cuttable. They can be changed and broken with the side effect of producing a massive release of energy. Physicists kept probing the atom and found that sometimes a nucleus captures a neutron and becomes more stable. In 1938, German physicists Otto Hahn and Fritz Strassmann found the opposite could happen. They found that if a uranium nucleus captures a neutron and gains enough energy, it can become so unstable that the nucleus splits into 2 lighter, roughly equal-sized nuclei, releasing a new neutron in the process. Lise Meitner and Otto Frisch explained that the uranium nucleus is like an electrically charged drop of liquid that starts oscillating when it captures a neutron, so much so that it oscillates itself right apart. Seeing the parallel with cells splitting, they termed the reaction nuclear fission. It wasn't long before scientists realized that the new neutron could hit another uranium atom and trigger the same reaction, again and again in a chain. But the chain reaction is the story we're going to save for another day. In writing this video, I not only had so much fun going over how the atom was uncovered, but I love how fantastic a model this is of the scientific process. It's amazing to step back and see how scientists collaborated over centuries, building on each other's work to discover the atom. This is what science does. To return to the all-important figure that is Isaac Newton, he has the famous quote written in a letter to Robert Hooke in 1675, "If I have seen further, it is by standing on the shoulders of giants." And I wanted to highlight this deliberately at the end because I think if you're still here, you'll hear me out, because we're moving somehow away from trust in science. According to a 2023 Pew Research study, only 57% of Americans would say that science has benefited society, which is insane when you consider something so seemingly ordinary like, according to the Bureau of Labor Statistics, 90% of Americans have a microwave in their home, which is made of science. It's a commercial use of Allied radar technology developed in the Second World War. I don't think anyone will deny the atom's existence, even if you can't see it. We know elements exist. Everyone knows water is H2O. We know they made the bomb. So why do we believe something we can't see, the atom, because the surrounding evidence is so strong, but ignore things we can see, even when there's just as much strong evidence? After the polio vaccine was introduced and widely accepted, polio deaths in the United States dropped to nothing. Vaccines kicked measles down to minuscule case levels. It was actually considered eradicated in the United States in 2000. But declining vaccination rates has brought measles back, and cases are rising rapidly because people are suddenly saying their social media education on vaccines and viruses outweighs decades of research and evidence. We're in a very weird era where the distrust in science is coupled with a scary rise in misinformation, largely propagated through AI-generated content and uninformed non-experts who speak with commanding authority. At best, it's a nuisance. At worst, it's manipulating people and obscuring information we need. Experts are experts because they bring a lifetime of study to their work. No one on this journey into the atom walked into a lab one day and started making pronouncements about electrons and subatomic anythings. Every scientist builds on previous work, verifies their results, and collaborates with partners. Science works for a reason. I know I can't convince anyone, and if you're still here, you're not someone that needs convincing, which probably makes this whole wrap-up needless. But maybe you've got someone in your life who you wish could see the value and importance of science, and maybe this line of thinking could help. Ultimately, as someone passionate about education and science literacy, I can't not try to tease out a little bit of a life lesson from history right now. If you've stuck with me through my little 2 cents, I really appreciate you. And if you liked this video, give it a like and a sub to the channel to help me not drown in the AI-filled algorithm waters. And if you really like this video, consider supporting my Patreon or becoming a member so I can keep making content. And you can also have access to my private Discord channels. I have long-form videos like this going up every few weeks. They take a long time to write and edit, but in the meantime, I post a lot of shorts to keep the content flowing, so stick around for more. I also need to give a shout out to Greg Gabor for chatting with me about the physics history. His book, Invisibility, deals with a lot of the stuff we've talked about today, and it's a lot of fun. I've linked it in the description if you want to check it out, and I've also added it to my science reading list on my Amazon storefront. And also shout out to my dad for giving this script a read and helping me verify the tough points. I just want to point out, as we talk about trusting experts, that I checked with a professor and a doctor to make sure the science in this video was right. Alright, that's going to do it for me today. Science is good. See you guys in the next one.